live.
All right, let's do it. Let's do this. Oh shit.
You working? Double checking?
Yeah. Yep.
All right, should we start?
We're on. Yeah, let's do it.
All right. Hello, everyone, and welcome to today's brand new episode of Corecast. I am your host, Tim.
Mikey.
And this is Sahil. Welcome, everybody, to a brand new, exciting episode of Corecast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to them. So without further ado, let's get to it. So Tim and Mikey, I remember when I took like even high school physics, college physics and stuff, and learned about the photon, the particle of light that transmits the electromagnetic force, learned that it was like massless. And I recently saw a video that called that into question, and we can go over like different examples of that and whatnot of that the video gives. But like asking the question, like, is the photon truly massless? Now, before we get to that question, I want to break it down. So, can we give the audience a like brief description of like what is mass at like a high level without going too deep into it?
Yeah, sure. Mass, um, like I guess the way we first learn about it in high school, like, is in terms of this other word called inertia, but then it's not always clear what that means. But basically what it means, it's like how difficult is it to change the motion of an object. So like if I want to push a very massive rock, it's very difficult to push it, to change its speed. But if I have a less massive rock, like a very like a pebble or something like that that has very low mass, it's very easy to change the speed of this object. So mass is basically how difficult it is to change an object's velocity. So it's basically how much force do I have to apply to change this object's velocity. So if something was like infinitely massive, it would take an infinite amount of force to change its velocity even a little bit. And the idea is that if something is completely massless, if it has no mass at all, then it would take zero force to send this thing moving as fast as it's possible to move.
Gotcha. Any thoughts on that definition, Tim, or would you say that's a fairly encapsulates it
Yeah, I think
at a
that
high level?
encapsulates it. Yeah, and if you want to make it a little more complicated, mass is really it's just a built-in parameter that connects energy and motion. Basically, if you buy into Einstein's theory of relativity, so the difference between something that's massless versus something that's massive is that if it's massless, then like Mikey was saying, then it takes no energy to move it at all. That means it's when something is massless, it is forced to move at the maximum speed. That is the speed of light. And if
Mm.
something is massive, that means it has the capacity to change its motion, to slow down, and it also means that that object can actually stop moving. You can slow it down to the extent that it stops, right? So there's actually a huge dichotomy between something that's
Mm.
massive versus something that's massless. It dictates the possibility of moving at the speed of light or not.
Mhm. So I want to kind of dig a little bit into the notion of something massless. So like for instance, in this discussion we'll touch on particles of light being massless, but let's assume for the moment that they're massless. They move at the speed of light. And Mikey, you said if something is like if something is massless, it won't take like that much for me to change its stuff. So why can't I like change the speed of light? Like why can't I just like smack it and just like stop it? Or like
Okay,
what's good?
that's a good question, right? Yeah, so one of the things that I wanted to mention also is that, yeah, something that's massless can never be stopped. It has to always be in motion. And like when I was confused about this, I used to just think about it this way. I guess first you have to accept the fact that you can't move infinity miles an hour. There's no,
Mm.
yeah, there is a cosmic speed limit, which we call the speed of light. And once you accept that, you could ask the question like, well, what if I did try to take like a massless particle, like a photon or something. Imagine I tried to get it to stand still, right? Or let's say I had a really, really, really tiny mass and I could get it to stand still. Then even the slightest gust of wind will set this thing moving, you know, as fast as it can possibly go. So basically, as the mass of a particle gets smaller and smaller and smaller, it gets really, really difficult. It gets more and more difficult to make it stand still because even the slightest, tiniest, most infinitesimally small push will send it speeding as fast as it's possible to move. So then when you take that limit to where the mass is actually zero, then it takes essentially zero force to get this thing moving uh, at the speed of light
Yeah.
or at the cosmic speed limit.
I think there's also another way to think about it mathematically, right? Like we know mathematically, like infinity is sort of like an ill-defined object. If you take infinity and you subtract a little bit, you still get infinity. And the speed of light is kind of like the infinity in the speed limit. So if you're moving at the speed of light, it's kind of like you're moving at an infinite speed. So even if you try to slow down a photon a little bit, you take a little bit away from infinity, it's still infinite, right? So basically you can't slow down a photon because it's already moving at that maximal speed. So you can't really slow it down. That's another way to think about it.
That makes sense. I guess so then so coming to the example of a photon, it's moving at the maximum speed, which or purportedly the maximum speed, which is the speed of light. I guess can we spend a little bit of time talking about like I mean, we covered this in a previous episode, but for new listeners coming in, can we differentiate between like the concept of the speed of light and the speed at which light moves? I know that was kind of a mouthful, but those two distinctions.
Yeah, I mean, so when Einstein proposed his theory, we have this concept of speed of light and proposed that light moves at that speed. And that is because of what we know as the Maxwell's equation. Maxwell's equation governs electromagnetism. And theoretically, if we know that, theoretically, if we assume that the light does not have a mass, then it is forced to move that at that speed. So there's a concept of the cosmic speed limit, right? And technically, it could be different from the speed of light, right? But if we assume that light has no mass, which is the assumption in Maxwell's equation, then we get that light moves at that cosmic speed limit. So that's why, in colloquial terms, these two concepts got combined together. The speed of light and the cosmic speed limit become one and the same thing. But experimentally, remember, physics is always an experimental science. Nature doesn't care what your theoretical prejudice is. Sure, maybe your theory says that the light has no mass, right? It doesn't have to be practically, right? Like what if light is just a teeny wee bit slower? Maybe it just moved just a tiny, tiny bit slower, which is so small that we couldn't measure it just yet. Then these two concepts could be different. The speed of light could be different from the cosmic speed limit.
Well, let's be clear. No one uses the word cosmic speed limit ever in physics, which annoys me because I think that should be the proper word for it.
Mm-hmm.
And as Tim mentioned, like the speed of light. So what we know is that there is a cosmic speed limit, and for totally accidentally historical reasons, physicists just call that the speed of light.
Right.
The topic of this podcast is addressing the question of whether or not light actually moves slower than the speed of light. Yeah, we should really just change the name speed of light to cosmic speed limit because it's just happened to be that light was the first particle we discovered that moves at the cosmic speed limit. So the cosmic speed limit, what should have been called the cosmic speed limit, got named the speed of light.
Yeah, that makes a lot of sense. I mean, I assume because they found that light moves, like the light was the first particle that moved or purportedly moves at the speed limit, cosmic speed limit. They found now other particles that also move at the speed limit, but this is no longer just restricted to light. Is that fair?
Yeah, totally. That's exactly what happened.
Gotcha. Okay, so then I guess like coming to this, there seems to be this like I don't know if I want to say like correlation, loosely speaking, between like the mass of a particle and how close it is to moving at like this cosmic speed limit. So it comes down to essentially what you're saying is that if you have a very, very small mass takes a little bit for it to move at like the maximum speed, and as it approaches zero, takes less and less effort essentially. And so if now the question is like, I guess, we all see in textbooks that like the photon has no mass, but now coming to the crux of this episode, like, does it have mass? Like, what does it mean if it has mass, and or how do we know it's massless?
So, so there are actually multiple effects, right? So the most obvious effects is what we've been describing. If the photon has a mass, then it can move at speed lower than this cosmic speed limit. But then this is also energy dependent. So depending on the energy of a photon, it can move at different speed now. And we know that the faster something moves, the more energy it has. So it would mean that for a photon that has very, very high energy, like gamma rays, it would have speed that's a lot closer to the cosmic speed limit. And for photon that has lower energy, like radio waves, then it might just move a teeny wee bit slower. Right? So that's the first leading order effect that one might observe if the photon has a mass.
Okay, but for those of you who don't know what gamma rays and radio waves are, basically it's saying that different colors of light would be moving at different speeds. Like if that would be the consequence of the photon having a mass.
Oh, that is interesting. Okay, before we discuss any experiments and stuff, if the photon did have mass, would that impact any of our cosmological measurements, like of how old the universe is, because then the speed would be different, or is it not meaningful?
So
Oh yeah, it would affect everything. Tim can probably talk more about that.
yeah, so of course it would affect everything, but we know from experiments that if light has a mass, it has to be so small that probably a lot of cosmological things won't be affected. So I guess the answer to that question is both yes and no, right?
Well, it would have to be ridiculously small to not affect
Right, yeah.
anything.
Yeah, I guess a better way to answer this is that yes, of course, it will affect the cosmology, but we know because we know what the cosmology of the universe is. If light has a mass, it will wreck so many things. The fact that a universe is the way it is means that if light has a mass, it has to be so small that it does not affect the cosmology.
So I guess like, do we, kind of taking a step back, do we know for a fact if light is massless, or is that like, is there some upper bound that we know and it's like it's practically massless as far as we can tell experimentally, or what's the nuance there?
I think the nuance is that, like, science, like everything is known to within some error limit,
Mhm.
right? Like science can't isn't the business of making exact answers or quote unquote proving facts, right? It's about getting error bars smaller and smaller and trying to be more and more precise and trying to be more and more confident about something. And so there's always wiggle room. If you say that something is like black or white, like you can't prove that it's exactly white, right? They're just like it might be just
Mhm.
so close, but yeah, there's like always some limit, and that's where people play these games. That like there is some room for it to be,
Mhm.
for it to have some mass, as long as that mass is like 0.0000000000000000000, like going on, like it's kind of like a game.
Yeah,
I
I think
I
in
don't
terms
think you
of
said enough zeros, Mikey.
in terms of kilogram, I think they're somewhere around 50 to 60 zeros. So you have a long way to go, Mikey.
Yeah, I gave up. I saw.
That's fair. That's fair. I guess like what would the upper bound on this, if it were to have a mass, would be like 10 to the minus 50 kilograms. Is that, Tim, am I understanding that
It's
correctly?
somewhere
Just
around that.
approximately?
It's somewhere around that ballpark. It's very tiny. And but then I want to give the audience a little bit of intuition what that looks like. And it's actually not that foreign because remember that light, the speed of light, the speed at which light moves in air is actually slower than the cosmic limit. So in some sense, light when it's in air actually kind of has a mass.
No, that's just because it's bouncing around stuff.
Right. But you can kind of interpret it that way. And some of the effects you see is like, for example, rainbows, right? it's telling you that different colors move at different speed. So when it bounces off when it bounces off a water molecule, it turns into rainbows. So that's roughly the things you can expect. The universe will look kind of like a little hazed out rainbow, except those colors will be like gamma rays and radio waves. So it's not so crazy, right? This concept, just to give some intuitions.
I see. I see. So what you're saying is like an analogy, maybe not, exactly word for word, but an analogy is like as if the universe contains this like, say loosely speaking, this medium, some kind of abstract medium, and light is moving through it, and you can think of it slowing down that way, or like what I'm just trying to understand the analogy with rainbows.
Yeah,
Yeah, I think just yeah. Sorry, go ahead.
yeah, I think that's absolutely correct. Like the way to interpret it, if let's say one day we did in fact found out that hey, light does have a mass, it's not zero, then there will be something like a medium, not exactly like air, but something. I hesitate to say it's not an ether, but it's some kind of quantum field probably.
Yeah, it would mean that space-time itself acts as a medium for light.
Oh, interesting, interesting. So I guess, Tim, what experiment would I need to design to convince you that light has mass? Like, what would you need to see? Like, how would we know?
There are actually two types of experiments. I will only talk about the first one first, and then we'll discuss the second one later. The first type of experiments is basically trying to see these rainbow effects. The idea is imagine you have let's say some quasars or whatever, something out really far away in the universe that's very violent, that's exploding, that's emitting gamma radiation, really high energy photons. The idea is you just stare at that stuff to see if you can see this rainbow pattern, to see if the high energy light travels faster than the lower energy light, right? If light truly is massless, doesn't matter what the energy of the light is, they would move exactly at the speed of light. But if they have a little mass, there will be what we call a dispersion, like a discrepancy between different frequency of light that travels. But then none of this discrepancy has been observed. So that places one of the most stringent bounds. I don't know if it's the most stringent bound on the mass of photon. And the number is like, depending on the experiments, it's like, 50 zeros, in kilograms, something like that.
So what you're saying is like, if you were to see a meaningful difference, you would expect in these like very violent bursts of radiation, so-called gamma ray bursts, which are like really, really bright. I don't know, some orders of magnitude brighter than the sun for some period of time. You would expect to see like a difference in the speed of those photons versus other photons. Is that correct?
Yeah. Like for example, if sometimes a gamma ray burst might be followed by, well, I guess you can look at the profile of the gamma ray burst. You usually a burst will have lights of different color, just like the light from the sun. So within that profile, there should be discrepancy. If photon has a mass, then you'll see this rainbow effect, but none is observed.
Gotcha. You mentioned a second experiment, Tim. What would that be?
Yeah, I want to know what that is too.
Oh, that's actually interesting. So remember that the connection between light, the speed of light, and the cosmic limit originally come from what's known as the Maxwell's equation. Basically, James Maxwell cooked up this equation, and he discovered that electromagnetic radiation, basically forces having to do with charges and magnets, somehow had this property that it can propagate. Yeah. And later on, this propagation was identified as the particle of light, right? And by making that identification, they identify, hey, look, the speed at which light moves matches this cosmic speed limit. But it turns out that if light has a mass, James Maxwell's equation will have to be modified. Yeah, that means the forces between electric charges and magnetic fields will have to be different. So imagine you take two magnets, the attractive forces would just differ by a tiny bit if the photon has a small mass. And this deviation could be measured.
Well, yeah,
Mm,
it would deviate a tiny bit from what? From what we know the relationship is between charges and the force?
Yeah. So you can
Oh.
right. So you can build a theoretical model, and mathematically there's this there's these lingo like the Coulomb force or whatever. You can measure roughly the force between magnets will the further away they are will be proportionally decreased by the square of the distance. It's the mathematical law. But if photon has a mass, that relationship will be different just by a tiny bit.
People do these experiments?
Well, okay. So the idea, yeah. So you could do it.
Sounds really hard.
So 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 interestingly, people have done these experiments, and they have very powerful magnets. But actually, the most powerful magnets, guess what it is? Well, actually, maybe it's not the most powerful. The largest, right? You have to look at
the,
large distance. It turns out to be Well, I guess
The
yeah.
Earth?
Any guesses?
Oh.
the sun.
Actually, the sun is pretty, well, but it's hard to measure. Well, it tends to be the Earth, right? These planetary magnetic fields, they're so well measured, and if you believe, you can model them appropriately using how the magma flows, these actually also you can use that to see if photon has a mass, and it turns out that those people also don't see deviations, and I think those are actually give you a few more zeros in the limits of the mass of the photon.
Wait, I was gonna ask which experiment is like more powerful at measuring whether or not the photon has a mass?
I don't know. I don't know which exactly, but I think the
I
planetary
gotta think
magnetic
that the really?
the planetary magnetic field is more powerful, just a bit, I think.
But there's so many more like uh
Gamma burst, gamma ray burst.
it just seems way more complicated.
Yeah.
What?
So what I'm hearing is that this experiment would involve taking like powerful magnets or maybe something involving the earth or some type of source of electromagnetic force, and then measuring if this force deviates from what we compute via massless photon, and see if the photon does have a mass, it'll impact the force in this small particular way, and then based on that, you'll be determined what the mass of the photon is to a certain level of precision. Am I understanding that correctly?
Yeah, but that's what we call a little more model dependent, right? Like, in order for you
Hmm.
to believe the results, you kind of have to be like, well, I think we understand how the magma on Earth is moving.
Yeah, that's what I
You
mean.
know,
That seems crazy.
well, I think people have a good understanding. But if you don't believe that, from the astrophysics side, the gamma ray burst, I think it's what we would call model independent. Because really,
Hmm.
you're not measuring directly the speed of light. You're just measuring the discrepancy between light of one energy versus another energy, and that's very much more powerful.
Hmm. That makes sense. I guess like I guess I'm curious how you would measure like the time difference, like when what, because these objects are very distant, a gamma ray burst happens, and then you'd have to know like what time it's at, but you're using other objects that emit light to determine what the time is, right? So I guess like how would you be able to keep track of time accurately?
I'm not sure about the details, but probably for light, there's like phase differences or the time. I think just the raw timing difference is enough. I think like I
Hmm.
mean you can probably at least time it within the seconds, and I'm sure with good instruments you can do much better. Right? It's like a camera basically. You can. I guess it has to be a really fast camera.
Hmm.
I don't know the details. I'm not sure.
It probably is a phase. I mean, you got to think that like if different colors are moving at different speeds, the farther away the object is, the more of a discrepancy you'd see. So the fact that these
Oh,
things
I
are
see.
happening like like millions and millions of light years away,
Hmm.
makes it much more powerful.
Yep. Probably the details,
Mm.
yeah, will be the distortion in the electromagnetic waves themselves, and that's
Mhm.
I mean I'm not an experimentalist. There's probably a lot of nuances and subtleties that probably too complicated for theorists to tackle. But yeah, the devil will be in the details, I imagine.
Yeah. So is it just a question of having more precise measurement to be able to answer this question, or like, is this something that like you wouldn't bet money on us being able to answer?
Well, we'll never be able to truly answer, right? All we can like just in terms of like philosophy of science, right? The most we can do is add zeros, add more zeros to the upper bound of what it could be.
Mhm.
So yeah, it's weird. I don't know. I guess people are always going to want to play this game,
But
right? See how
yeah,
many zeros they can add.
but as theorists, right? I think it's it's as good of a zero as we'll get, and I think it's zero.
Yeah, yeah.
So in your mind, you guys are happy to just call it zero and call it a day, kind of a thing,
Yeah, for sure.
from
Like,
a
and
theoretical
also
standpoint.
like the experimentalists try to measure if it maybe does have a mass, and then on top of that, you have theorists that try to like think of theories like, oh well, because like the simplest theory, like as Tim mentioned, like just Maxwell's equation, and its various generalizations, they point towards something that is massless. The theory is simple, it's pretty, it's elegant, it's all that. Like if you give the photon a mass, suddenly the theory becomes complicated and horrible and ugly, and um it's that's why I feel like it's kind of like a game. It's like those games that like kids play where it's like, oh, like, I know you are, but what am I? There's like, it's kind of like they're just doing it for the sake of doing it.
I see. I see. Does okay, if the photon did have a mass, would that, besides like Maxwell's equations that we've referenced a number of times in this episode, would that like break special relativity, general relativity, or like any one of these like foundational theories of physics?
I don't think it would break relativity.
I think it's not a necessity. Okay, like
Yeah.
relativity
Mhm.
can accommodate a photon that has a mass, but of course you could always try to break relativity. But no, but you'd be crazy as a theorist to do it because relativity is a
Mhm.
beautiful theory. It's got lots of symmetries which is something we hold sacred in physics.
Mhm.
And if there's no reason to break it, why break it, right? Like you can have a massive photon and still have relativity. It's just that the relationship between space and time won't be called the speed of light anymore. It would just be called the cosmic speed limit. It would just be a name change, I say.
Which is what it should be called right now.
Yeah.
Yeah. Does this same argument, so we've been talking about the photon because that's the most I guess most widely known particle that moves presumably moves at the speed at the cosmic speed limit or close to it. But for some of the other particles which we don't necessarily need to get into the names of, that we theoretically say move at the speed of light, i.e. are massless. Does the same argument hold for those particles as well? Like, are they
Sorry, which
truly
argument?
massless? Are
Oh.
are other particles that we say theoretically move at the speed of light or are massless truly massless, or does it follow the same argument?
Well, for most of those particles, aside from the other problem with those other particles is that we can't really access them or even measure them. The photon is one of the most easily accessible and measurable particles in the
Mhm.
whole toolkit or whatever, in the whole zoo of particles that we know about. Um, yeah, all of the other ones would be very, very difficult to probe experimentally. Well, actually, maybe not. Maybe that's not true, right? Because like maybe you could do things similar to like that magnetic field of the Earth. Maybe you could do experiments similar
Yeah,
to
I mean,
that.
I would say the photon is a little special.
Mhm.
Like sure, you can argue maybe the lightest neutrino doesn't have a mass, but it might I can't recall the physics. Maybe that's not possible. But we know that all the neutrino have masses. I don't remember if there are limits on the lightest one. It probably has mass. But anyway,
We know we know the ratios though. So
the difference,
and
the
so
mass difference, yeah. But
yeah.
but then another thought I want to bring up is that the photon is a little more special. Like if neutrinos didn't have mass, we'd be like, okay, sure. But for the photon, which is what we call a force carrier, there's a special status when it doesn't have a mass, right?
Mhm.
And when it doesn't have a mass, there's a beautiful symmetry. There's a beautiful mathematical structure that emerges. And if you create a mass, that kind of gets wrecked a little bit. So the photon is a little special theoretically in that way.
Well, all of the force carriers, all of what we call like force carriers that have long range effects, they all in the simplest version of the theory, the most elegant version of the theory, have this property where they should be exactly massless, and that principle is like very much at the core of like the standard model of particle physics and quantum field theory. And yeah, if you give those things a mass, you just wreck. You just do great violence to all of that beautiful machinery. So
Oh, that sounds like a theoretical bloodbath.
yeah.
With the mass of a photon. So we actually have an audience question. Does string theory predict a mass for the photon?
I would say no. There's no such
No.
prediction.
Okay.
Actually, string theory is very happy to have objects like photons that are totally massless. In fact, probably multiple ones. And I think in string theory, the photon would correspond to some, because string theory predicts really curled up dimension. It would just kind of predict at least one direction in those curled up dimension is free to move. It doesn't really have a mass. Well, I don't know the exact details, but string theory is very happy to have a massless photon, I think.
Gotcha. So we're almost at time. So I wanted to give you guys a chance to leave the audience with any parting words or life lessons from a photon's perspective, whether it weighs a lot, check its weight on a bathroom scale, but let me know.
Give you go first. I'm having trouble.
Well, I mean, I would say the mass of a photon is probably a good question to ponder experimentally, because physics is an experimental science. Doesn't matter how good your theories are; it has to match with theoretical predictions. But as a theorist, I'll be truly surprised if we find a mass for the photon. So I think, is it truly massless? Well, yeah, we can't find out, but it's as good of a zero as I think physics can get. I mean, it's got 50 zeros in front of the kilogram. I think that's pretty good for me. I think so. For practical purposes, the photon is massless. I think we can say that.
Yeah, maybe I'll just, at the risk of offending someone who might be working or thinking about these things, like, it's. I wouldn't say that trying to establish this is like a high priority in terms of like funding. Like there are other more interesting questions that we can ask. And sure, yeah, if you have the resources to investigate this, why not try to see how many zeros you can get on that. But how many zeros will it take for people to be satisfied? I don't know. Because this is like a never-ending game you can play with almost every single question. Yeah, I'll just stop at that.
Yeah, I actually, Tim, one question I have for you. This is slightly veering us a little bit off topic. Is like the cosmological constant's like 120 zeros, right? So like, how does that compare to the mass of a photon?
Well, the units are a little different. I guess you have to take the fourth root. I think because energy density depends on units.
I see.
So let's see, 120 zeros, take the fourth root. Yeah, maybe
It's like 30 zeros.
Yeah, but I don't remember the units. It's in terms of Planck mass. I have to do some calculation, but I feel like the limits on the mass of the photon is smaller.
Oh, okay.
Probably.
Okay.
Yeah.
Okay. All right then. Well,
don't take my word for it, but my money will be on that number as close to zero as possible. All right. Cosmological constant, we know it's not zero. So
yeah. Okay. That's That's fair. That's fair. All right then. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.